Chapter 1. What defines a year? Across the cosmos. Before we can grasp the strange and stretched years of dwarf planets, we must first understand what a year truly is, not just for Earth, but across the universe. On our planet, a year is defined by one full orbit around the Sun. It takes approximately 365.25 days, giving rise to our calendar and the familiar cycle of seasons. But this definition, while useful for Earthlings, is only one version of a cosmic truth. A year is an orbit in essence. A year is simply the time it takes for any celestial body to complete one full revolution around its parent star. This period varies depending on a planet's distance from that star and the gravitational forces in play. The farther a planet is from its star, the slower it travels, and the longer its year becomes. This is not a theory. It's a natural consequence of Kepler's third law, which tells us that orbital periods grow with distance. On Mercury, closest to the Sun, a year is just 88 Earth days. On Neptune, it stretches to 165 Earth years. But dwarf planets? Their years often defy intuition, bending time into immense spirals of patience, the shape of time. In space, while Earth's orbit is nearly circular, dwarf planets often follow elliptical orbits, elongated paths that take them on vast looping journeys around the Sun. These orbits are shaped not only by their distance, but by orbital eccentricity, how stretched the path is, and by gravitational nudges from larger planets. This means that a dwarf planet doesn't move at a constant speed. It may spend centuries creeping through the farthest parts of its orbit, then swing swiftly through the inner regions before retreating once more into the cold. Some even tilt dramatically out of the flat plane that most planets follow, adding another layer of complexity to their celestial clocks. Time without seasons. Another key difference is the absence of Earth-like seasons. Most dwarf planets are so far from the Sun that they receive only faint light and heat, barely enough to create significant atmospheric change. Some, like Pluto, have thin, transient atmospheres that collapse and reform as they drift closer to or farther from the Sun. So while we measure our years by the turning of leaves, the tilt of the Earth, and the changing light in the sky, dwarf planets mark time silently, through icy motion and long frozen arcs. Why it matters. Understanding the length of a year on these distant worlds is more than an exercise in astronomy. It's a glimpse into the structure of our solar system. It helps us map the gravitational influences that shaped the planets, trace the early history of planetary formation, and even hint at the possibility of unseen forces, like hypothetical planets or the gravitational pull of dark matter. The year, then, is more than a measurement. It is a story of movement, rhythm, and cosmic architecture, a heartbeat of the solar system itself. As we journey deeper into this exploration, we will meet each dwarf planet in turn and uncover how long their years truly are, and what those years reveal about the hidden harmonies of our universe. Chapter 2. Pluto, the outcast with the endless year. In the distant reaches of the Kuiper Belt, far beyond the familiar orbits of Neptune and Uranus, drifts a small icy world once hailed as the 9th planet of our solar system. Pluto, beloved, debated, and endlessly mysterious, is where our journey into the long years of the dwarf planets begins. A world rediscovered. Discovered in 1930 by Clyde Tombaugh, Pluto was, for most of the 20th century, considered the outermost planet of our solar system. Its size and dimness made it difficult to observe, but its existence stirred the imagination. For generations, Pluto was the symbol of the unknown, a distant beacon of mystery at the edge of the Sun's reach. But in 2006, the International Astronomical Union redefined what it means to be a planet, and Pluto was reclassified as a dwarf planet. It wasn't a demotion in significance, but rather an evolution in understanding. Pluto didn't shrink. Our knowledge expanded. How long is a year on Pluto? A single year on Pluto, the time it takes to complete one full orbit around the Sun, lasts about 248 Earth years. That means if you were born on Pluto, you'd never see your first birthday. In fact, Pluto has only completed about 1/3 of an orbit since its discovery nearly a century ago. This incredibly long year is a result of its great distance from the Sun. Pluto's average distance is about 5.9 billion kilometers, and its orbit is highly elliptical. Sometimes it even comes closer to the Sun than Neptune, a phenomenon that last occurred between 1979 and 1999. During those years, Pluto was the 8th planet from the Sun, not the 9th. An eccentric and tilted orbit. Pluto's orbit is one of the most unusual in the solar system. It doesn't follow the same flat, circular path that most planets do. Instead, it's tilted at an angle of 17 degrees to the plane of the solar system, and follows an elongated ellipse that brings it much closer to the Sun at perihelion and much farther away at aphelion. This eccentricity means that the speed of Pluto's orbit varies drastically. When it is near the Sun, it moves faster. When it is farther, it slows down. It is a celestial dance governed by Kepler's laws, and the result is a year that unfolds in slow, uneven rhythms. Shadows and sunlight. Despite being so far from the Sun, Pluto isn't entirely in darkness. Its surface reflects light due to the presence of nitrogen, methane, and carbon monoxide ices. At its closest approach, the faint sunlight is still about 900 times dimmer than what we experience on Earth. Enough for shadows, but not for warmth. During its long orbit, Pluto's tenuous atmosphere of nitrogen and methane can partially freeze and fall to the ground when it is far from the Sun, only to resublimate into gas as it draws closer. This rare atmospheric cycle means Pluto's year brings not just motion, but transformation. Time as a landscape. To imagine a year lasting 248 Earth years is to step outside the human scale of time. Empires rise and fall in the span of a single Plutonian season. Snow can fall and remain frozen for centuries. A single sunrise might herald changes that unfold slower than memory itself. Pluto's year teaches us patience. It reminds us that not all orbits are swift, not all rhythms are short. Some stories take centuries to tell. As we leave Pluto behind and venture further into the outer solar system, we will meet even stranger bodies with slower spins and wider orbits, each one offering a different lesson in the meaning of time. Chapter 3. Eris, the distant rival with a colossal orbit. Beyond even the orbit of Pluto lies another icy world, darker, colder, and more massive. Its name is Eris, and it played a pivotal role in reshaping how we classify planets. With an orbit that defies simplicity and a year longer than any we've encountered so far, Eris is a dwarf planet whose existence rewrote astronomical history. The discovery that changed everything Eris was discovered in 2005 by astronomer Mike Brown and his team at the Palomar Observatory. At first, Eris appeared to be larger than Pluto, and that caused ripples through the scientific community. Was this the 10th planet? If Pluto was a planet, how could we not grant the same status to Eris? The answer would become one of the most controversial in modern astronomy. Rather than adding a 10th planet to our system, the International Astronomical Union chose to create a new category, the dwarf planet. Eris didn't dethrone Pluto. It clarified the rules of the solar system. In doing so, it helped us see the cosmos with sharper eyes. Eris's majestic year on Eris, the time it takes to complete a full orbit around the Sun, lasts approximately 558 Earth years. That's more than twice as long as Pluto's year. Eris travels along a long, narrow and inclined orbit. At its farthest point from the Sun, it is nearly 14.6 billion kilometers away. At its closest, it still lies well beyond Pluto's reach. For comparison, light from the Sun takes over 13 hours to reach Eris, compared to just over 8 minutes for Earth. When we speak of time on Eris, we're not measuring days or months. We're speaking in generations, in centuries. The orbit of Eris is slow, deliberate and cold, a journey through an almost silent part of space where sunlight fades to a whisper. A frozen surface of light and shadow. Despite its distance, Eris has a surface that reflects nearly all the light it receives. This high reflectivity, or albedo, is due to a frost of methane ice that covers its crust. In the dim sunlight, Eris shines like a frozen mirror. And yet, its environment is one of the coldest known. Temperatures can plunge to 243 degrees 6. This makes Eris not just distant in space, but removed from any familiar experience of warmth or light. No spacecraft has ever visited Eris, and its surface remains largely mysterious. What we do know comes from telescope data, mathematical modeling, and the slow accumulation of patient observation. The companion moon Eris has a tiny moon named Dysnomia, after the daughter of the Greek goddess Eris. This moon helps us understand the mass and orbit of Eris itself. Dysnomia's steady revolution offers a gravitational fingerprint, revealing that Eris is about 27% more massive than Pluto, even though it's slightly smaller in diameter. This greater mass plays a role in shaping its orbital behavior. Eris moves, with a steadiness befitting its weight, tracing a massive ellipse through the outer solar system. Time as isolation if time on Pluto felt elongated. On Eris, it feels nearly still. One orbit takes more than 5 human lifetimes. A person born on Eris would never live to see the completion of even a small part of its solar journey. In fact, no civilization in human history has lasted the length of a single Iridian year. This profound isolation isn't just physical, it's temporal. To exist on Eris is to be cut off from the solar rhythm we know. seasons, years, and even the concept of a calendar lose their meaning. And yet, Eris orbits with quiet purpose. It continues its journey through the Kuiper Belt, invisible to the naked eye, but ever present in the solar symphony. As we turn next to Haumea, a dwarf planet unlike any other, fast, oblong, and spinning like a cosmic top, we will discover that not all distant worlds are slow. Some dance to their own rhythm, spinning with unexpected urgency even in the frozen dark. Chapter 4. Haumea, the spinning oval of the Kuiper Belt. In the distant outskirts of our solar system, among the icy relics of creation, spins a dwarf planet that breaks the mold, not only in shape but in motion. Its name is Haumea, and unlike the slow, steady revolutions of Pluto and Eris, Haumea is in constant rapid rotation. Where others drift, Haumea dances. Discovery and unusual. Shape Haumea was discovered in 2004 by two separate teams, one from the United States and Cher, another from Spain, resulting in a brief debate over naming rights and discovery claims. Ultimately, the object was named after the Hawaiian goddess of childbirth and fertility, symbolizing its role in producing a family of smaller celestial fragments. But what truly makes Haumea unique is its elongated shape. Unlike the spherical appearance we associate with planets, Haumea resembles a spinning American football or a stretched egg. This bizarre shape is due to its incredible rotation rate, a full spin every 3.9 hours, making it one of the fastest spinning large objects in the solar system. Haumea's year. Fast spin, slow orbit. While it rotates quickly, Haumea orbits the Sun much more slowly. Its year lasts about 284 Earth years, placing it between Pluto and Eris in terms of orbital period. It travels on a moderately elliptical path, remaining roughly 6.5 billion kilometers from the Sun on average. This means a Haumean year is a long, quiet journey through space, but with a body that never stops spinning. Imagine a world where a single day is over in just under 4 hours, but where the entire journey around the Sun spans multiple human generations. A crystalline surface, Haumea's surface, is covered in crystalline water ice, suggesting a surprisingly young and dynamic crust, possibly replenished by cryovolcanic activity or past collisions. Its bright icy surface reflects a significant portion of sunlight, and its high albedo is another factor that helped astronomers detect it in the first place. Haumea is believed to have undergone a massive collision long ago, a cosmic impact that likely led to its odd shape and fast rotation. This event may also explain why Haumea has a family of smaller Kuiper Belt objects sharing similar composition and orbital characteristics. In a way, Haumea is not alone. It exists in a gravitational kinship. Haumea's moons and mysterious. Ring Haumea has 2 moons, named Hiyaka and Namaka, after the daughters of the Hawaiian goddess. Their movements help astronomers estimate the mass and internal structure of Haumea, which is believed to have a rocky core beneath its icy shell. In 2017, astronomers made a surprising discovery. Haumea has a ring system. This makes it the first known Kuiper Belt object with a ring, an astonishing find for such a distant world. The ring lies in Haumea's equatorial plane, aligned with its rapid spin, and may be composed of debris from that ancient impact. Time warped by motion Haumea teaches us that time can be experienced in strange ways. A day so short that the world seems in constant motion, paired with a year so long it feels like an epic voyage. If you lived on Haumea, the sky would change slowly, but your days would blur past like flashes in the cold light. It reminds us that planetary time is not uniform. It is sculpted by motion, by mass, by impact, by tilt. Time on Haumea is elastic, stretched between the pull of gravity and the push of momentum. As we leave Haumea's shimmering surface behind, we turn to another intriguing world, Makemake, a dwarf planet with secrets still hidden in its reddish frost, where the mysteries of its orbit and seasonal changes may unlock deeper truths about how time moves in the dark. Chapter 5. Makemake, the reddish enigma of the outer solar system. Floating in the remote stillness beyond Neptune, there is a lonely, reddish world that remains mostly hidden from our view, a dwarf planet known as Makemake. Though less well known than Pluto or Eris, Makemake is one of the brightest objects in the Kuiper Belt, reflecting the pale sunlight with a strange, ruddy sheen. This enigmatic world holds within it ancient secrets of frozen methane, shifting light, and time stretched out over centuries. Discovery and naming Makemake was discovered in March 2005 by a team led by astronomer Mike Brown, just days after the discovery of Eris. It quickly became clear that Makemake was large enough to qualify as a dwarf planet, and like its icy cousins, it challenged our understanding of planetary classification. Named after the creator god of the Rapa Nui people of Easter Island, Makemake reflects both the mystery and creativity of the cosmos. It is a name tied to fertility and the origin of life, an appropriate symbol for a distant body that still holds secrets about how the solar system came to be. How long is a year on Makemake? Makemake completes its orbit around the Sun once every 305 Earth years. That makes its year longer than Pluto's, but shorter than Eris's. Its orbit is elliptical, though not as dramatically stretched as Eris's, and it lies in a region filled with icy primordial objects. From the viewpoint of Earth, Makemake's movement is glacially slow. Even after nearly 2 decades of observation, it has barely crept across the sky. This immense timescale makes it hard to track seasonal changes or long-term evolution. The rhythm of Makemake is simply too slow for a single human lifetime. A reddish surface, rich in mystery. Makemake's most distinctive feature is its reddish surface, likely caused by the presence of tholins, organic compounds formed when ultraviolet light and cosmic radiation interact with methane. These compounds stain the icy surface with hues of red and brown, creating a canvas unlike anything seen on Earth. This gives Makemake a somewhat alien appearance, despite the fact that it is composed mostly of familiar materials like methane and nitrogen ice. It's also one of the brightest objects in the Kuiper Belt, second only to Pluto, thanks to its high reflectivity. Yet, strangely, it was long thought to be moonless, making it difficult to calculate its mass or density. For years, Makemake existed as a riddle with no companion. A moon emerges d'Entour. 2016, astronomers discovered that Makemake does indeed have a small, Dark Moon, Mk2. This elusive satellite had remained hidden due to its faintness and close proximity to Makemake's bright surface. The discovery of Mk2 allowed scientists to begin measuring the mass of Makemake more accurately and to hypothesize about its internal structure. While still many questions remain, this companion moon has opened a new chapter in our understanding of Makemake's gravitational field and orbital dance. Seasons in slow-motion Makemake has a high obliquity, meaning it's tilted dramatically on its axis. This suggests that the dwarf planet could experience extreme seasonal changes. But these would unfold so slowly, over hundreds of Earth years, that no single observer could ever witness a full cycle. Imagine a summer that lasts for decades, followed by a winter that stretches into the next century. These are the kinds of seasons that shape Makemake's surface over eons, as gases sublimate and refreeze, subtly reshaping its outer crust. This temporal dilation, the sense that time flows differently here, adds to the surreal nature of life on a world like Makemake. Glimpse into the early solar system Makemake offers a preserved look at the solar system's early building blocks. Its frozen, methane-rich surface and slow, sweeping orbit are a time capsule from billions of years ago. Every grain of ice, every trace of tholin, every slow movement through the stars is a relic of our cosmic beginnings. Makemake doesn't just mark time, it holds it. It invites us to see the universe not in hours or days, but in epochs. As we continue on this journey, we turn now to a lesser-known object in the Kuiper Belt, one not yet officially classified as a dwarf planet, but no less fascinating, Gong-Gong. A world with a strange name, a stretched orbit, and hints of a deep internal mystery. Chapter 6. Gong-Gong, the distant giant with a slanted spin. Far beyond Neptune, hidden in the dim corners of our solar system, moves a reddish ice world unlike any other, Gong-Gong. With a name drawn from Chinese mythology, and an orbit that defies convention, Gong-Gong is a relatively recent arrival in our astronomical awareness, yet it has quickly claimed its place among the great icy wanderers of the Kuiper Belt and beyond. Discovery and identity Gong-Gong was first observed in 2007 by astronomers searching the edges of the solar system. Initially known by the designation 2007 OR10, this object was notable not just for its size, but for its deep red hue and extremely slow rotation. In 2019, it was officially named Gong-Gong, after the Chinese water god known for causing floods and tilting the earth. Fittingly, this celestial Gong-Gong also has a tilted axis and a mysterious past, echoing the mythology it's tied to. Though it's not yet officially recognized as a dwarf planet by the International Astronomical Union, most scientists include Gong-Gong in that category due to its size and spherical shape. It is currently the fifth largest trans-Neptunian object known, larger than Makemake, and close in size to Eris and Pluto. Gong-Gong's year, a massive elliptical lupin. Of Gong-Gong's most remarkable features is its highly elliptical orbit. It takes an astonishing 554 Earth years to complete one journey around the Sun, among the longest orbital periods of any major object in the outer solar system. Its orbit is not only long, but highly inclined, meaning it doesn't follow the same flat plane as most planets and dwarf planets. Gong is a true wanderer, taking a slow, skewed path that keeps it far from the warmth of the inner planets for centuries at a time. For those standing on its icy surface, if that were even possible, the concept of a year would become abstract. The seasons, the cycles, the passage of time itself would stretch into unfathomable scales. A world of ice and red-colour Gong is reddish in colour, similar to Make and Qua, and this tint likely comes from tholins, complex organic molecules created by the interaction of solar radiation with methane. These materials coat the surface and give it an ancient, weathered look. Spectral analysis shows that Gong likely has frozen methane, water ice, and possibly even ammonia on its surface. This suggests that its interior may once have been warm enough to host cryovolcanic activity, and that subsurface oceans might still exist, deep beneath layers of frozen rock and ice. A moon named Xiangliuin. 2016, astronomers discovered that Gong has a moon named Xiangliu, after the nine-headed serpent companion of the mythological Gong. This small satellite orbits its parent body at a relatively close distance and has helped researchers estimate Gong's mass and density. Interestingly, Gong's rotation is very slow. A full day on this dwarf planet lasts about 44 Earth hours. This sluggish spin is likely the result of tidal interactions with Xiangliu, meaning the moon's gravitational influence is dragging Gong into a slower rhythm, much like Earth's moon affects our tides. Time in the shadows on. Gong, time unfolds in shadows. A single year outlasts entire human civilizations. A single day moves like a forgotten tide, pushed gently by a silent moon. The cold light of the sun barely reaches this distant realm, and the stars loom brighter in the black sky. Here, the cycles of time don't follow the pulse of human experience. They echo instead the ancient rhythms of cosmic migration. Slow, steady, solemn. Gong challenges us to imagine a solar system where movement is almost imperceptible, where gravity and distance conspire to stretch time into cosmic decades. Preview of deeper realms. As we leave Gong's dark and drifting orbit, we prepare to venture deeper still, into the territory of minor worlds that stretch the limits of our definitions and expectations. Next, we will explore the icy mystery of Quawa, a dwarf planet candidate with its own secrets, moons and rings, and a year shaped by its unique path through the Kuiper Belt. Chapter 7. Quawa, the ringed wanderer of the Kuiper Belt. In the vast, frigid outskirts of our solar system, nestled within the Kuiper Belt, lies a world that blends ancient myth with modern discovery, Quawa. Though it doesn't yet hold official dwarf planet status, many scientists regard it as one of the solar system's major icy bodies, and recent revelations have made it one of the most fascinating. This is a story not only of time measured in centuries, but also of a strange ring, system that defies all expectations. Origins and naming discovered in 2002 by astronomers at the California Institute of Technology, Quawa was one of the earliest large Kuiper Belt objects to be identified after Pluto. Its discovery helped challenge the classical definitions of planets and fueled the discussions that eventually led to Pluto's reclassification in 2006. Quaoar is named after the creation deity of the Tongva people, the original inhabitants of the Los Angeles basin. In their mythology, Quaoar sang and danced the universe into existence, a fitting image for a body that orbits in serene rhythm at the edge of known space. Quaoar's year, a long icy cycle. Quaoar orbits the Sun once every 288 Earth years, placing its path in a similar range to that of Haumea and Makemake. Its orbit is moderately elliptical and slightly inclined, keeping it firmly within the Kuiper belt, but distant enough to remain untouched by the inner solar system's dynamics. Time on Quaoar stretches beyond the familiar. Generations could pass before a single revolution is complete. Its year is a quiet loop through the dim halo of our solar system, a frozen journey untouched by warmth or seasons as we know them. Surface composition and shape Quaoar's surface is a mosaic of water ice, methane, and possibly ammonia hydrates, suggesting that it may have had internal activity at some point in its history. Despite being hundreds of kilometers smaller than Pluto, Quaoar appears nearly spherical, giving it a shape consistent with hydrostatic equilibrium, a key criterion for dwarf planet classification. Its reddish hue indicates the presence of tholins, formed by the interaction of cosmic rays with methane on its surface. These organic materials tint the ice and suggest a world that has aged in isolation for billions of years. The surprising ring system. In 2023, astronomers made a stunning discovery. Quaoar has a ring system. Unlike Saturn's brilliant rings, this one is dark and faint. But it stands out for another reason. It lies far outside Quaoar's Roche limit, the zone where planetary rings are traditionally believed to exist. This challenges long-standing theories of how and where rings can form. The ring may consist of icy debris or fragments from past collisions, and its stability remains a topic of active study. Its unexpected position raises questions about the gravitational dynamics and internal history of Quaoar, and how such a structure can remain intact so far from its host. This tiny, icy world may be rewriting the rulebook on planetary rings. Moon named Weywot Quaoar is accompanied by a small moon called Weywot, named after the son of the god Quaoar in Tongva mythology. The moon's orbit allows astronomers to estimate Quaoar's mass, and has helped confirm its dense, rocky interior beneath the icy shell. Weywot's eccentric orbit adds complexity to the system, suggesting a past shaped by tidal interactions, impacts, or gravitational exchanges we still don't fully understand. Echoes of deep time standing on Quaoar, if one could. Time would feel eternal. The sky would be black, the stars sharp and unblinking. The sun, distant and small, would cast barely enough light to distinguish surface from shadow. Days would be long, years would be a lifetime. And above, a dark ring would silently trace its improbable arc, defying gravity's predictions. It would be a reminder that even in the coldest corners of the cosmos, surprises still await. As we prepare to journey further outward, we turn our gaze to another distant traveller, Sedna, a mysterious object whose journey around the Sun takes millennia. Sedna's year is not just long, it is mythic. Chapter 8. Sedna. the 1,000-year orbit of a frozen sentinel. Beyond the familiar landscape of the Kuiper Belt, in the quiet deep where sunlight fades into starlight, drifts a crimson wanderer, Sedna. With an orbit so vast it borders on the unimaginable, Sedna challenges our very concept of what it means to belong to the solar system. Its year spans more than 10,000 Earth years, a time frame so long it predates all of recorded human civilization. In many ways, Sedna is not just distant in space, it is distant in time. Discovery and the outer unknown, Sedna was discovered in 2003 by a team led by Mike Brown, who had also identified Eris and Makemake. Almost immediately, astronomers realized that Sedna was something extraordinary. It was far beyond Pluto, far beyond Eris, and moving along a strange, elongated orbit that couldn't be easily explained. It didn't fit neatly into any known category. It was too far to be a typical Kuiper Belt object, and yet not far enough to be part of the distant Oort cloud. Sedna seemed to exist in a no-man's land between classifications. Named after the Inuit goddess of the sea, who resides in the cold depths of the Arctic Ocean, Sedna is the perfect symbol for a celestial body that drifts in isolation, surrounded by the icy silence of space. Sedna's year, 11,400 Earth years. Sedna holds the record for one of the longest orbital periods of any known solar system object. Its orbit takes it from a perihelion of around 76 AU, astronomical units, still twice as far as Pluto ever gets, out to an aphelion of nearly 1,000 AU. That means Sedna's year lasts approximately 11,400 Earth years. To put that in perspective, when Sedna last reached its closest point to the Sun, woolly mammoths still roamed the Earth, and the last ice age was beginning to recede. When it returns to that position again, humans as we know them may have evolved into something entirely different, or vanished altogether. It is a cosmic relic, a time traveller on an orbit shaped not by planets, but possibly by stars. Origins beyond the solar system. One of the most fascinating aspects of Sedna is the mystery surrounding its orbit. It's simply too far out to have been influenced solely by the known planets. Its trajectory suggests the possibility of an encounter with another star early in the solar system's history, or perhaps the gravitational pull of an unseen massive object, a hypothetical Planet 9. Some astronomers believe Sedna may have been captured from another solar system altogether, a wandering object snared by the Sun's gravity billions of years ago. If true, it would mean that Sedna is not just distant, but alien. A red, icy world, Sedna's surface appears deep red, possibly the result of tholins, the same complex organic molecules found on Makemake, Quaoar, and other distant bodies. Despite being smaller than Pluto, Sedna is large enough to be considered spherical, and may contain a mix of rocky material and volatile ices under its frozen crust. Due to its extreme distance, Sedna is incredibly cold, with surface temperatures estimated to be below 240 dig or 400 dig. There is virtually no solar warmth, and no known moons or ring systems to help unravel its mysteries. It is a world of silence and darkness, but also of endurance, a fossil of the solar system's earliest days. Beyond the edge of the known Sedna lies in a region some call the inner Oort cloud, a transitional space between the Kuiper belt and the even more distant shell of icy bodies that may surround the solar system in all directions. If true, Sedna may be only the first of many similar objects awaiting discovery. Studying Sedna could provide clues not only about our solar system's formation, but about the galaxy's role in shaping it. Each step of Sedna's orbit is a data point from a cosmic story that has yet to be fully told. Time, stretched into eternity, to witness a year on Sedna would require more than a dozen millennia. Human history, from the dawn of agriculture to space exploration, would all occur in the span of just one orbit. Here, time itself takes on a mythic quality. Sedna doesn't move to the rhythm of seasons or centuries. It drifts on a path of geological epochs, carved by forces older than any life on Earth. As we leave Sedna's distant orbit, we return slightly closer toward the Kuiper belt, to a dwarf planet with its own dramatic history of collision and renewal. Haumea, the elliptical, fast-spinning body with rings and mystery to spare. Chapter 9. Haumea, the spinning shard of the outer solar system. Nestled within the Kuiper belt, Haumea stands apart from every other dwarf planet, not for its size or orbit, but for its shape, speed, and story. It is a cosmic enigma, elongated like an American football, spinning faster than any other known large object in the solar system, and surrounded by rings and moons born of violence. With a year lasting centuries and days that last mere hours, Haumea reminds us that time and shape in the cosmos are fluid, moulded by history and motion. Discovery and designation. Haumea was officially discovered in 2004, although it was the subject of some controversy between two research teams. Eventually named after the Hawaiian goddess of fertility and childbirth, Haumea is fittingly associated with the concept of creation, both in mythology and in its likely collisional origin. Its two moons are also named after Haumea's daughters, Hiaka and Namaka, preserving the celestial family connection. These moons, along with Haumea's unique ring system, suggest a violent past, perhaps the shattered aftermath of a giant cosmic impact. Haumea's year, 284. Earth years. Like many of its Kuiper belt siblings, Haumea's orbit takes it far from the Sun, requiring 284 Earth years to complete a single solar revolution. Though long, this is relatively typical compared to the extended years of Sedna, or Eris. Haumea's orbit is slightly elliptical and moderately inclined, making it a stable but distant participant in the Sun's gravitational dance. For a being on Haumea's surface, if such life could exist, the passage of time would be unrecognizably slow. Seasons stretching across entire generations, the fastest spin. What makes Haumea truly exceptional is its astonishing rotation. A day on Haumea lasts just 3.9 Earth hours, making it one of the fastest spinning large bodies in the solar system. This rapid spin has caused Haumea to become significantly elongated, with an oblong shape more akin to a rugby ball than a sphere. Its extreme rotation is believed to result from a massive collision in its early history, which also likely created its moons and left behind a trail of icy debris. This fast spin also causes equatorial bulging, a distortion of Haumea's structure that makes its shape deviate dramatically from hydrostatic equilibrium, even though it qualifies as a dwarf planet due to its gravitational rounding in at least one dimension. The discovery of a ring in 2017, astronomers detected a ring system around Haumea, the first of its kind ever observed around a trans-Neptunian object. The ring orbits at a distance of about 2,300 kilometers from the center of Haumea and is relatively thin, but it further enhances the dwarf planet's uniqueness. Its presence again supports the idea of a violent origin, possibly the result of material flung into orbit by its spin or impact debris that coalesced into a stable band of icy particles. Haumea's surface and composition. The surface of Haumea is covered in crystalline water ice, unusually bright and reflective compared to other Kuiper Belt objects. This brightness suggests that the surface is relatively young and geologically active, or at least frequently resurfaced by some process, perhaps through sublimation or cryovolcanism. Underneath the icy shell, Haumea likely contains a rocky core, giving it a higher density than Pluto or Eris. This rocky makeup, combined with its outer ice, hints at an interior that might once have been warm enough for differentiation, or perhaps even subterranean oceans in the distant past. Time, warped by rotation Haumea, represents a strange contradiction. While its year is long, its day is dizzyingly short. This creates a unique experience of time, where the surface rotates rapidly through endless days, yet the orbit, the greater loop, stretches across centuries. In this dual rhythm, time is both a spinning blur and a frozen cycle. For astronomers, Haumea is a natural laboratory for studying angular momentum, collisional formation, and the mysterious mechanics of ring formation in deep space. Toward the farther edge, as we leave Haumea's brilliant, fast-spinning world behind, we venture again toward the dark reaches, to the icy distant orb named Eris, once thought to be the 10th planet, whose discovery changed the definition of planet itself. Its orbit is wide, its surface cloaked in frozen nitrogen, and its year among the longest in the solar system. Chapter 10. Eris, the dwarf planet that redefined the solar system. In the cold, dim outskirts of the solar system, beyond Pluto, beyond Haumea, beyond almost everything, resides a distant world whose discovery reshaped how we define a planet. Eris is not only one of the most massive known dwarf planets, but also one of the most consequential. Its year spans over 5.5 centuries, and its presence forced scientists to ask a very difficult question. What exactly is a planet? A historic discovery, Eris, was discovered in January 2005 by a team led by astronomer Mike Brown, who also discovered Makemake and Sedna. When Eris was first observed, its brightness and distance led astronomers to believe it might be even larger than Pluto, and thus a new planet. For a short time, Eris was unofficially referred to as the 10th planet. But that changed everything. The astronomical community realized that if Pluto and Eris were both considered planets, then dozens, perhaps hundreds, of similar icy bodies would also qualify. The result? In 2006, the International Astronomical Union, IAU, redefined the term planet, and both Pluto and Eris were reclassified as dwarf planets. Thus, Eris didn't just claim a title. It sparked a revolution. Eris's year, 558 Earth years Eris, takes approximately 558 Earth years to complete one orbit around the Sun. Its highly elliptical path brings it as close as 38 AU, astronomical units, and as far as 97 AU, well beyond Pluto's most distant point. Eris is currently near its aphelion, meaning it's about as far from the Sun as it ever gets. For any potential observer on Eris, the Sun would appear as a tiny, blinding star, no larger than a pinhead in the sky. Daylight would be pale, shadows long and deep, and a single orbit, a single year, would take longer than 5 human lifetimes. Time here is vast, slow, and eerily silent. Composition and surface Eris is about 2,326 kilometers in diameter, making it just slightly smaller than Pluto. However, Eris is denser, implying a greater proportion of rock beneath its icy shell. Its surface is believed to be coated in frozen nitrogen, methane, and possibly carbon monoxide, which reflect sunlight and make Eris one of the most reflective objects in the solar system, almost as bright as freshly fallen snow. This reflectivity, known as albedo, is a clue to the surface's chemical purity and low age. The lack of darkening from cosmic radiation suggests the surface may be resurfaced regularly, either by seasonal processes or cryovolcanic activity. At surface temperatures nearing 243 degrees Celsius, 405 degrees Celsius, Eris is among the coldest known objects orbiting the Sun. Dysnomia, the silent companion. Eris has one known moon, Dysnomia, named after the Greek spirit of lawlessness and daughter of Eris, the goddess of strife. Dysnomia's orbital characteristics have allowed astronomers to estimate Eris's mass with remarkable precision, confirming that it is about 27% more massive than Pluto. This moon's circular orbit suggests that the Eris-Dysnomia system may be ancient and stable, untouched by recent cosmic disruptions. A world of static and silence. If one could stand on Eris, the sky would be star-filled and utterly quiet. With its atmosphere, if any, frozen and collapsed onto the surface, there would be no wind, no weather, and no clouds. Just a frozen wasteland of glistening plains stretching beneath an unblinking sky. Seasons, if they exist, would unfold over centuries, and the landscape might change only as Eris slowly approaches the inner part of its orbit, receiving marginally more solar energy over decades. Eris exists in a realm of permanent twilight, where cosmic time flows like molasses. The distant queen once seen as a potential planet, Eris now reigns as one of the queens of the Kuiper Belt, cold and regal. It didn't dethrone Pluto out of malice. It simply reminded us that our solar system is bigger, stranger, and more nuanced than we ever imagined. As our journey continues, we turn next to a set of icy bodies orbiting beyond Eris, into territories where planetary years are still being defined and where mystery outweighs certainty. Chapter 11. Orcus, the mirror shadow of Pluto. The tapestry of the Kuiper Belt, where icy bodies drift in the twilight beyond Neptune. One object stands out for its remarkable gravitational harmony with Pluto. Its name is Orcus, and it is often called Pluto's anti-twin, because it shares a very similar orbit, but from the opposite side of the Sun. Though much smaller and dimmer than Pluto, Orcus orbits in quiet synchrony, like a shadow echo, moving in cosmic rhythm through a world of ice, silence, and slow time. Discovery and the name of the underworld Orcus was discovered in February 2004 by a team of astronomers, including Mike Brown and Chad Trujillo, as part of ongoing surveys of trans-Neptunian objects, named after a Roman god of the underworld. A counterpart to the Greek Hades, Orcus carries a name that reflects the cold, silent domain it inhabits. Its largest moon, discovered in 2005, is called Vanth, a mythological demon who guided souls to the afterlife, further anchoring Orcus in the pantheon of distant, deathly figures. A 247-year journey around the Sun, Orcus completes a full orbit around the Sun in approximately 247 Earth years, a period nearly identical to that of Pluto. However, the two never come close to each other. They are locked in a 2.3 resonance with Neptune, meaning that for every 2 orbits Orcus makes, Neptune completes exactly 3. What makes Orcus truly fascinating is that its orbit is mirrored to Pluto's. When Pluto is at its closest point to the Sun, perihelion, Orcus is at its farthest, aphelion, and vice versa. This cosmic symmetry has led many astronomers to refer to it poetically as Pluto's anti-planet. Despite this mirroring, the two bodies are not gravitationally bound. Instead, they dance in opposing arcs, held in place by Neptune's subtle pull. Composition and surface clues. Orcus is about 910 kilometers in diameter, less than half the size of Pluto, but still large enough to qualify as a dwarf planet. Its surface reflects modest light, suggesting a mix of icy and dark organic materials. Spectral analysis indicates the presence of water ice and possibly ammonia or methane ices, which hint at internal geologic activity in the distant past. Orcus's coloration is more neutral than Pluto's, lacking the distinctive reddish hue of tholins that dominate Pluto's surface. Temperatures here are estimated to remain near 230 degrees Celsius, 382 degrees Dwarf, with no known atmosphere and no significant variation in surface features, at least not yet observable from Earth. Vanth. A moon in the dark orbiting Orcus is a companion nearly half its size. Vanth, one of the most substantial dwarf planet moons discovered. The Orcus-Vanth system is especially intriguing due to Vanth's mass, which significantly influences the motion of both bodies. Some astronomers even speculate they might form a binary system, similar to Pluto and Charon. Vanth's surface is darker and redder than Orcus's, suggesting a different composition or origin. The two may have formed from a collision or capture scenario billions of years ago, and their slow orbital dance continues today in near-perfect synchrony. Studying Vanth gives scientists a rare chance to understand the gravitational mechanics of distant binaries in the Kuiper Belt, a system frozen in time, yet still rich with untold stories. The stillness of time, with a year lasting nearly 2.5 centuries, Orcus sits in a realm where change is measured in glacial pace. Eons pass in a single rotation of its orbital clock. If one could stand on its frozen surface and watch the sun inch across the sky, a full sunrise to sunrise would take days or weeks, and the concept of a season would lose all meaning. There is no wind, no erosion, no sound, just the slow creep of shadows on a world locked in ancient rhythm with Neptune and Pluto, a metronome marking time in one of the most remote sectors of the solar system. A twin in the shadows. Though Orcus may never gain the fame of Pluto, it serves as a silent twin, a balance point in the outer solar system. Studying Orcus gives astronomers a chance to explore how similar orbits produce vastly different geological outcomes, and how ancient resonances shape the evolution of planetary bodies over billions of years. Chapter 12. Leliakuhonua, the Voyager of 30,000 years. Far beyond the familiar planets, and even past the icy domain of the Kuiper Belt, there exists a realm where time itself seems to stretch into eternity. In this dim and distant place, a small, quiet traveller drifts on an orbit so vast that its journey around the Sun takes more than 30,000 Earth years. This mysterious object is known as Leliakuhonua, the one who flies far, in the Hawaiian language. Discovered in 2015 and catalogued as 2015 TG3H7, Leliakuhonua belongs to a rare class of detached trans-Neptunian objects known as extreme TNOs. These bodies are only loosely bound to the gravity of the Sun, and their elongated orbits suggest influences beyond what we currently see. Its discovery was a whisper from the outer darkness, hinting at something more, something massive and hidden, lurking at the edge of our solar system. Leliakuhonua never comes closer than 65 astronomical units from the Sun, more than twice the distance of Neptune, and reaches as far as 2000 AU at its most distant point. No human civilization has lasted long enough to witness a full orbit. The last time this tiny world was where it is now, mammoths still roamed Earth. The next time it returns to this region, our species may be long gone, or perhaps voyaging among the stars. Its size is modest, likely no more than 300 kilometers in diameter, and it reflects very little sunlight. We know almost nothing about its composition, rotation, or surface features. What makes Leliakuhonua so fascinating isn't what we see, but what it suggests. Many scientists believe that Leliakuhonua, along with a few similar bodies, may be under the gravitational sway of an unseen planet. Planet 9, a hypothetical, super-Earth-sized body orbiting far beyond Pluto. These objects seem to cluster in their orbital paths, as if shepherded by something massive and mysterious. In that way, Leliakuhonua acts as a cosmic compass, subtly pointing toward a larger hidden presence. But whether this unseen planet exists or not, Leliakuhonua serves as a reminder that the solar system is not a closed story. Its edges are not boundaries but invitations to look further, to wait longer, to dream bigger. A year on Leliakuhonua lasts longer than all of recorded human history. In the dark silence of the outermost solar system, time flows differently, like the slow breath of the cosmos itself. As it floats in the deep, its orbit is not a circle, but a spiral across epochs, an ancient loop that dances through the ages, quietly watching civilizations rise and fall from the edge of everything we know. And perhaps in that silence, Leliakuhonua waits, not just for light, but for wonder. Chapter 13. Chaos, the silent giant of the outer belt. In the frozen outskirts of the Kuiper Belt, where shadows stretch long and the stars shimmer like distant memories, there resides a mysterious and massive body named Chaos. Discovered in 1998 and officially designated 19521 Chaos, this trans-Neptunian object is one of the larger members of its domain, yet it remains remarkably overlooked. Chaos is aptly named after the primeval void of Greek mythology, from which all existence was born, and in many ways it lives up to that name. It orbits in a region where gravitational forces clash and balance, where ancient debris from the birth of the solar system continues its slow, circling dance around the sun. Its path is neither smooth nor predictable, but carved out over eons through the quiet resistance of ice and time. With a diameter estimated at 600 kilometers, Chaos is just shy of qualifying as a full-fledged dwarf planet, though some astronomers believe it might be one, depending on its shape and internal composition. Its orbit spans about 309 Earth years, placing it well beyond Neptune, but still within reach of our most distant observations. Unlike many Kuiper Belt objects with highly elliptical orbits, Chaos maintains a more stable, almost circular path, or anomaly in a region defined by extremes. This unique stability is what makes it so scientifically intriguing. It suggests that Chaos may have been part of the early architecture of the solar system, a primordial survivor from a time before the planets settled into their current orbits. We know little of its surface. It likely contains water ice, silicates and organic compounds, common among bodies in the outer solar system. But we have no direct images, no color data, and no confirmation of moons or rings. It floats through the void, unbothered and almost unseen, like a memory too old to place. A year on Chaos, lasting more than 3 human centuries, passes slowly in the chill silence of deep space. It moves with a kind of patience unknown to our world, gliding through a realm where the sun offers no warmth, only direction. Its journey is unhurried, vast and hauntingly quiet. Chaos reminds us that the outer solar system is still largely terra incognita. We think we understand gravity, formation, motion, but then a world like this appears, ancient, steady and silent, and we realize how much is left to learn. Out there in the cold, Chaos continues its path, a solitary witness to billions of years. It doesn't demand attention. It simply exists, a sheer relic of a time when our solar system was still in flux, still becoming. In a place where years last longer than lives, and silence speaks louder than discovery, Chaos spins on, a dark whisper of cosmic history written in slow motion. Chapter 14. Buffy, the tilted mystery of the Kuiper skies. Far beyond the orbit of Neptune, deep within the icy sprawl of the scattered disk, there drifts a small and silent world with a path unlike any other. Known to astronomers as 2004 X190, it earned the nickname Buffy, not for drama, but because of its surprising nature. This is a celestial body whose existence quietly defies the rules we thought we understood. Discovered in 2004 by a team scanning the distant edges of the solar system, Buffy measures approximately 500 kilometers in diameter, large enough to be spherical, possibly massive enough to be classified as a dwarf planet. But what makes Buffy truly unique is its orbit. Most planets and dwarf planets follow paths that lie close to the flat plane of the solar system, the ecliptic. Buffy, however, orbits the Sun at a sharp angle of 46.8 degrees, as if it had been tilted out of the shared alignment long ago. Its distance from the Sun remains consistently remote, hovering between 52 and 62 astronomical units, never drawing near the inner planets, nor venturing into the extreme isolation of objects like Sedna or Leleakuhonua. It travels in quiet isolation, making one full orbit around the Sun every over 440 Earth years. That means Buffy completes just 2 revolutions for every century of our modern calendar. In that time, civilizations rise, fall, and forget. Yet Buffy continues, steady and strange. What could cause such an inclination? That is the mystery. Traditional models of solar system formation don't account for such orbits. Some scientists believe that an early gravitational encounter with a massive passing body, perhaps a yet undetected planet, or even a rogue star in the Sun's birth cluster, may have kicked Buffy into its tilted track. Others suggest that it could be evidence of Planet 9, the elusive giant that might still be hiding in the darkness, sculpting the paths of distant bodies like Buffy. And yet, despite the intrigue, Buffy remains almost completely unstudied. We have no direct images, no known moons, no rotational data. It reflects only a faint fraction of sunlight, barely more than a smudge against the night. Its surface may be coated with frozen methane, nitrogen, or ancient water ice, but we can't yet say for sure. What we do know is that its very presence tells us our models are incomplete. Buffy challenges the idea of order. In a system once thought to be clockwork, it stands as an anomaly, a ghost of ancient gravitational chaos, or a harbinger of deeper truths yet to be uncovered. In the long, cold stillness of the Kuiper Belt, Buffy glides along its angled path, a sliver of mystery orbiting in slow motion. Its year is not just long in time, it's long in wonder. For in Buffy's strange tilt, we glimpse the possibility that our solar system is far more complex, more dynamic, and more poetic than we ever dared imagine. Chapter 15, 2012. VP 113, The Whisper of a Hidden Giant. In the frozen outer reaches of our solar system, beyond Pluto, beyond the Kuiper Belt, even beyond the familiar threads of gravitational order, there lies a world of shadows and speculation. This world is known as 2012 VP 113, or by its informal nickname, Biden. It is not large or bright, but it holds within its slow orbit a question that has haunted astronomers for over a decade. What or who is tugging at its path? Discovered in 2012 by astronomers Chad Trujillo and Scott Shepard, VP 113 was, at the time, the most distant object ever found in the solar system. Its perihelion, the point closest to the Sun, lies at 80 astronomical units, twice as far out as Neptune, and farther even than the famous Sedna. At its most distant, VP 113 drifts to over 400 AU, far enough to make Earth's orbit feel like a cozy fireside circle. A single year on VP 113 takes over 4,300 Earth years. Since the dawn of human civilization, since the construction of the pyramids and the earliest strokes of writing, it has not yet completed even one loop around the Sun. It moves so slowly, so patiently, that its orbit is more like a frozen echo than a rhythm. VP 1-13 is small, likely around 450 kilometers in diameter, and reflects little sunlight. Its surface is thought to be coated with a layer of ice laced with complex organic materials, reddened by cosmic radiation, unchanged for eons. But it is not its surface that fascinates scientists. It is its trajectory. When VP 113 was discovered, astronomers noticed something strange. Its orbital path was eerily similar to that of Sedna and other distant objects. They were grouped in a way that defied randomness. It's as if some unseen hand had arranged them, pulling their orbits into alignment. That hand, perhaps, belongs to something massive, something we have not yet seen. This led to the revival of the Planet 9 hypothesis. The idea that a super-Earth-sized planet, lurking far beyond Pluto, could be shaping the orbits of distant trans-Neptunian objects, like VP 113, through its unseen gravity. If true, it would mean our solar system is far from fully mapped, and that a new planet waits in the cold, waiting to be found. But VP 113 also stands alone. It has no known moons, no companions, and no close encounters. It is solitary by nature, a drifting point of data in the black. And yet it speaks volumes. It tells us that something is out there. Something massive enough to bend the trajectories of icy worlds across tens of thousands of years. In the dark quiet where light barely reaches and time flows slowly, VP 113 glides forward. It has no atmosphere, no weather, no known activity, only motion. A gentle glacial arc through space, like a whisper from the ancient past. A year on VP 113 is not something we can measure in memories, but in myths. It is a calendar for the cosmos itself, too vast for human reckoning. Yet even from this distance, it touches our curiosity. And in its silent path, it may yet reveal the location of a hidden giant, a long-lost neighbor watching from the edge of night. Chapter 16. Farot, a pink world in the deepest cold. In the dim and distant reaches of the solar system, where sunlight weakens into a pale whisper and time seems to move differently, there floats a lonely traveller named Farot. Officially catalogued as 2018 VG18, this frozen object was once the most distant solar system body ever observed. Discovered in the quiet of December 2018, over 120 astronomical units from the Sun. To put that into perspective, Pluto orbits at roughly 39 AU. Farot is more than 3 times that distance. So far, in fact, that light from the Sun takes nearly 17 hours to reach it. And out there, in the deep freeze of interplanetary space, Farot moves with unimaginable slowness. Astronomers estimate that a single year on Farot, one full orbit around the Sun, could take well over 1,000 Earth years. Its trajectory is so vast and its distance so extreme that we've only observed a small arc of its motion. Much remains uncertain. We don't yet know its full orbital path, its inclination, or how far it might eventually drift. It is a mystery in motion, a celestial echo unfolding across centuries. Despite its distance, Farot offers surprising clues. It reflects more sunlight than expected for such a remote object, suggesting a surface brightened by ice and fresh frost. Its faint pink hue reveals the presence of complex organics, molecules irradiated and altered over millions of years, giving it a rosy, ethereal appearance. It is not just cold, it is beautifully cold. Unlike more famous bodies like Eris or Makemake, Farout is not large. Estimates place its diameter around 400 to 500 kilometers, possibly enough for hydrostatic equilibrium, though it remains unconfirmed as a dwarf planet. It has no known moons and no visible atmosphere, just silence. Silence and distance. The discovery of Farout wasn't merely a triumph of observation, it was another nudge toward the unknown. Along with Sedna, Lilekuhonua, and 2012 VP-113, Farout's orbit hints at something more. An unseen gravitational force, perhaps Planet 9, might be shaping these extreme orbits, clustering them in a way that can't be explained by the known planets alone. Farout could be a puzzle piece in a much larger, invisible framework. And yet, even without answers, Farout is significant. It tells us that the edge of the solar system is not a sharp border, but a misty frontier. A place where the sun's rule fades but never ends. A place filled with ancient frozen relics that drift quietly through cosmic winter. Farout reminds us that there are places so distant, so isolated, that they've barely been touched by the warmth of creation, yet they endure, orbiting on timelines longer than recorded history. They are not forgotten. They are waiting. So as Farout continues its slow, solitary path through the frozen dark, it becomes a symbol of cosmic patience. A pink, icy lantern, flickering at the far edge of what we know, quietly urging us to keep looking outward, toward the silence, toward the stars, and toward whatever still lies hidden beyond. Chapter 17. Farout, a pink world in the deepest cold. In the dim and distant reaches of the solar system, where sunlight weakens into a pale whisper and time seems to move differently, there floats a lonely traveller named Farout. Officially catalogued as 2018 VG-18, this frozen object was once the most distant solar system body ever observed. Discovered in the quiet of December 2018, over 120 astronomical units from the Sun. To put that into perspective, Pluto orbits at roughly 39 AU. Farout is more than 3 times that distance. So far, in fact, that light from the Sun takes nearly 17 hours to reach it. And out there, in the deep freeze of interplanetary space, Farout moves with unimaginable slowness. Astronomers estimate that a single year on Farout, one full orbit around the Sun, could take well over 1,000 Earth years. Its trajectory is so vast and its distance so extreme that we've only observed a small arc of its motion. Much remains uncertain. We don't yet know its full orbital path, its inclination, or how far it might eventually drift. It is a mystery in motion, a celestial echo unfolding across centuries. Despite its distance, Farout offers surprising clues. It reflects more sunlight than expected for such a remote object, suggesting a surface brightened by ice and fresh frost. Its faint pink hue reveals the presence of complex organics, molecules irradiated and altered over millions of years, giving it a rosy, ethereal appearance. It is not just cold, it is beautifully cold. Unlike more famous bodies like Eris or Makemake, Farout is not large. Estimates place its diameter around 400 to 500 kilometers, possibly enough for hydrostatic equilibrium, though it remains unconfirmed as a dwarf planet. It has no known moons and no visible atmosphere. Just silence. Silence and distance. The discovery of Farut wasn't merely a triumph of observation. It was another nudge toward the unknown. Along with Sedna, Leleaku Honua, and 2012 VP113, Farut's orbit hints at something more. An unseen gravitational force, perhaps Planet 9, might be shaping these extreme orbits, clustering them in a way that can't be explained by the known planets alone. Farut could be a puzzle piece in a much larger invisible framework. And yet, even without answers, Farut is significant. It tells us that the edge of the solar system is not a sharp border, but a misty frontier. A place where the sun's rule fades but never ends. A place filled with ancient frozen relics that drift quietly through cosmic winter. Farut reminds us that there are places so distant, so isolated, that they've barely been touched by the warmth of creation. Yet they endure, orbiting on timelines longer than recorded history. They are not forgotten. They are waiting. So as Farut continues its slow, solitary path through the frozen dark, it becomes a symbol of cosmic patience. A pink, icy lantern, flickering at the far edge of what we know, quietly urging us to keep looking outward, toward the silence, toward the stars, and toward whatever still lies hidden beyond. Epilogue. Time beyond time. We began this journey with a question, one that seems so simple, so small. How long is a year on a dwarf planet? But as we drifted deeper into the outer solar system, past the icy echoes of Pluto, beyond the whispering rings of Haumea, and into the frozen mystery of Sedna, we discovered that this question opens the door to something far greater. Each dwarf planet, each distant body, carries within its orbit a different rhythm of time. Some trace long ellipses over centuries. Others dance quietly in isolated loops, untouched for millennia. A year on these frozen worlds is more than just a number. It is a testament to cosmic patience, to the enduring structure of a solar system that moves on a scale far beyond our own. They orbit in silence, their surfaces scarred by ancient impacts coated in methane, nitrogen, and time itself. And yet, though no spacecraft has yet set foot upon many of these distant worlds, they pull us toward them, not just with gravity, but with wonder, with the need to understand where our solar system ends and what might lie beyond. For every name, Eris, Orcus, Gongong, Sedna, Farut, there are likely dozens more still waiting in the dark. Some may be small and silent, others may be shepherded by something massive and hidden, and all of them together remind us that our home star is just one light in a vast and ongoing story, a story that reaches out to the edge of night. In the end, perhaps the real lesson isn't how long a year is out there, but rather how deeply time stretches when we dare to look further. How softly the universe speaks when we finally learn to listen. And how much beauty lies in a single, silent orbit through the cold. Thank you for drifting through the stars with us. Until next time, stay curious and sleep among the constellations.